We're ready to get started. So, in all of our previous lectures, we introduced lots of terms, including like what is bonding, how to describe a chemical bond, what is conformation, what is stereochemistry, chirality, how to assign our stereo configuration, etc. Acid-base chemistry, right? What is a Bronsted acid? What is a Bronsted base? What is a Lewis acid? What is a Lewis base? How to identify acidity by looking at stability of the conjugate base. So today is going to be a transition lecture trying to answer the question, like why did we learn all these things that we covered before? Like why do we care? And how does that link to chemical reactions? So I'm trying to teach you organic chemistry from the perspective of organic reaction mechanism, aka by understanding how this reaction is taking place, you can predict how the reaction outcome is without memorization of every single reaction that you saw. All right, so today I hope it's gonna be a link between all the vocabulary that we learned, and today you can think about it as a grammar class. And starting from our next lecture, we'll start to look at actual reactions of alkenes, alkynes, haloalkenes, or general substitution reactions, etc. We'll start to write sentences. All right, so everything before today are vocabulary. We learn all the vocabulary. Today, we're trying to learn the grammar, linking everything together. And from Friday's lecture, we'll start to write sentences from these vocabulary and grammar. All right? So this is not any specific chapter in your textbook. I think they claim this arrow pushing to be like an appendix inside the chapters. So that's what we're going to do today. In general, today we're going to go over arrow pushing of a bunch of elementary steps in organic chemistry. That includes dissociation of a chemical bond into anions. You have formation of polar covalent bonds, so dissociation and formation of your chemical bond, substitution reaction, and also addition reaction. So these are like more elementary steps that can take place in organic chemistry reactions. So that's an arrow pushing of these processes. That's first goal. Second goal, we'll review the kinetics and thermodynamics of chemical reactions on these potential energy diagram. And also, before we jump into arrow pushing, I'm going to do a quick review on all the reactive intermediates we sort of mentioned, but never dive into like a standard like lecture note. So let's get started. First thing first, kinetics and thermodynamics of chemical reactions. So in all chemical reactions, like in this case, I'm just showing a one-step chemical reaction. Your reaction can be multiple step, meaning forming your B. You can have subsequent transition state taking place, and then your B becomes an intermediate. Right, so in chemical reactions, we're normally talking about two different factors controlling the chemical reaction output. One, we call this to be the thermodynamic control. So this is the one we went over in detail in our acid-base chemistry. So thermodynamic control of a chemical reaction, we're talking about the relative stability of your reactant A to your product B. So in this case, the delta G, the difference between your A and B, the difference of Gibbs free energy, equals to negative RT ln K. And your K is your equilibrium constant, which is the concentration of your product over concentration of your reactant. All right, so that's thermodynamics. It tells you whether or not your product or reactant is the more stable species. However, only knowing the product B is thermodynamically more stable doesn't necessarily say the reaction takes place. So we have a different factor called kinetics. Or we have the rate of a chemical reaction to be a rate constant times the concentration of the reactant. All right, so the kinetics tells you how fast your reaction takes place. So it's very common, you can have a thermodynamically favorable reaction, but the rate of the reaction is so low, you'll never observe that reaction to take place. On the other hand, in reality, we are always facing the situation of selectivity. That is, in this case, for example, between your A to B, you could also have a potential formation of a compound C via a different transition state. All right, and then the selectivity of your chemical reaction is thus determined by either the kinetics or the thermodynamics or both of your reaction. And when we're talking about reaction mechanism, we're trying to understand these transition state and also the thermodynamic relationships so we can predict what is the reaction outcome. So that's the overarching goal of studying the reaction mechanism. Yes?
You mentioned like kinetics being favorable, the other way around, thermodynamics being favorable, but like kinetics wouldn't allow it to happen. Could it happen the other way where kinetics is?
Right, so that's a very good question. Let's imagine we have a kinetically very favorable process. Imagine we have a very low barrier process here, and we are forming a thermodynamically uphill product, right? So what's the result? So if this reaction can take place between A to D, with, let's say this one is my delta E1, you can also regenerate A from D. So the reaction may have a reversibility and thus becomes a thermodynamic controlled process because the kinetic barrier is so low. So we'll go over them case by case, but just keep in mind when we're talking about reaction mechanism, both kinetic and thermodynamic factors might be important. All right, so this should be a quick review in thermodynamics and kinetics of your Gen Chem knowledge. Again, just knowing these terminologies, we'll discuss them case by case. Secondly, before we go into the arrow pushing, there's another set of topic called reaction intermediate or reactive intermediates. So these are the things we've been seeing in previous lectures, but today I want to give it a quick summary of all the reactive intermediates that we discussed and the relative name of these intermediates, relative stability of these intermediates, how do we call it? So in general, when we have a carbon, let's say we have 4 different things attached to it. So these 4 different things can be your other atom, or it can be a hydrogen, right? And now let's imagine we're breaking one of these carbon bonds to form a reactive intermediate. Now your carbon only has 3 things attached to it. So you'll have different kind of reactive intermediate depending on how do you break that chemical bond. So imagine we have first way of breaking this chemical bond is both electrons in your chemical bond goes onto your carbon. So what does that mean? So that means we are having, let's say, for example, this is a hydrogen, and then you have a base, right? So the base grabs the hydrogen, and then both electrons in your CH bond goes onto your carbon. It's like an acid-base reaction. Your CH is your Bronsted acid. Now the resulting of this deprotonation will form a carbanion, right? So your carbon has 1 extra electron. It has a formal negative charge. And then depending on what are the things attached to the carbanion carbon, we have different names for these carbanion. So if you have 2 hydrogen and 1 R group, so R group being any kind of alkyl group, this one we call it a primary carbanion. Or you only have 1 R group attached to the carbanion carbon, so that's primary. Alternatively, if you have 2 R group attached to the carbon, or we also say this one is 1. This one is secondary carbanion. And sometimes you also see us writing it as like 2 with a little degree on there, so secondary. And we can have tertiary carbanion. So different R group, 3 of them. So that's my tertiary. All right. So carbanion, negatively charged species, and these are like primary, 1 R group attached to it, secondary, 2 R group attached to it, and tertiary, 3 R groups attached to it. When we talk about stability of the carbanion, the primary is the more stable one, and your tertiary is the less stable. All right. So most of these things, we sort of already mentioned them in previous lectures. I just want to summarize everything to make sure we're on the same page from now on. Next up, what if, likewise, I still have this tetrahedral carbon, 4 things attached to it. Let's do that, say that's a hydrogen. And now I'm breaking this CH bond to a different direction. So what we are forming is your carbon now have a positive charge on it. All right, so this kind of electron moving, I'm saying, okay, so we're deprotonate that hydrogen. So in this case, we then form a carbocation. All right, and likewise, for carbocation, depending on how many R group are attached to the carbocation where the positive charge is, you can have primary, secondary, and tertiary. So for primary, you have 2 hydrogen, 1 R group, so that's primary. You can have secondary, with 2 R group attached to it. And tertiary, when you have 3 different R groups attached to it. All right, and for the trend, for the stability of the carbocation, the tertiary carbocation is the more stable one. And your primary carbocation is the less stable. Yes?
Is R and R carbon either different or just not?
They can be different or the same, it doesn't matter, just some kind of alkyl group. Yes?
Why does the stability trend work?
The stability trend is different because in this case, we're missing electrons. So more R group there is able to stabilize the vacancy, right? In this case, we're having not enough electrons in the carbocation. But in the carbanion, we're having too much electrons. So more R group is destabilizing the carbanion. So the stability trend difference because we have different reactive intermediates. All right, so these are the two different kinds, and both of them are formed through two electron process, meaning the two electron in the original carbon, whatever bond, is being cleaved, and both electrons goes onto the carbon or go onto the other part. Actually, let me replace this with an X, it's more reality. And we have a third kind of intermediate called radical. So likewise, when we have, let's say, three different things attached to the carbon, and let's say now I have a peroxide on my carbon. So we can have a homolytic cleavage. So this kind of arrow you'll show indicating one electron process. So in the chemical bond, you have two electrons, right? So basically it says we're homolytic cleavage, that chemical bond. So one go to the left, one go to the right. What we end up forming is a single unpaired species. So that's called a radical. And likewise, depending on what are the things attached to the carbon with the radical, you can have primary, you can have secondary, and also tertiary radical. All right. And the trend of your radical stability is your tertiary being the most stable, and your primary being the least stable or less stable. Yes?
Is there supposed to be an electron for the secondary and tertiary?
Yeah, thank you for pointing that out. All right. And in our previous lecture, we were also talking about allylic carbocation, allylic carbanion, and allylic radical being more stable due to resonance stabilization. So the same applies to all three kinds of reactive intermediate. Resonance stabilization or delocalization of these, whether it's an anion, a carbocation, or a radical. So the resonance destabilization will stable these reactive intermediates. So far, so good. So, I mean, we went over all these like scattered all around in previous lectures, but I think today is a good thing when we try to summarize everything and make sure we're on the same page here. All right, so primary, secondary, tertiary describes how many R groups are attached to that center carbon with the active species on it. We have three different kinds of reactive intermediate: carbanion, negative charge; primary, more stable; carbocation, positive charge; tertiary, more stable; and radical, like a single unpaired electron; tertiary, more stable. Didn't get? Okay, sounds good. And now we're ready to start talking about elementary reactions and arrow pushing in these elementary reactions. So, getting started. The goal today is to talk about what are the potential puzzle pieces we can use when we're creating a reaction mechanism or a generalized reaction pathway linking your reactant to the product. First question here is, why do we ever care about the reaction mechanism? So the logic here is very straightforward. We can have multiple reactions taking place with the same mechanism. So that's telling us, like, if you understand the mechanism good enough, you do not need to memorize every single reaction. So an example here is electrophilic aromatic substitution. It's not covered in 30A, but this is one of the iconic equations that people give it different name. So the general reaction is like this. We have like an arrow ring. You have an electrophile, some kind of electrophile. We went over electrophile. It's like a slightly positive electron deficient species, and a X. And in here, the first step is we have the aromatic group attacking this chemical bond, or attacking the electrophile, breaking the EX bond to form this intermediate. Like, without knowing anything about it, if I show you what's the structure of your reactant, intermediate, and product, you know how to do the arrow pushing to link these structures. Again, arrow pushing is just telling you where the electrons is going. Like, for example, if I'm doing the arrow pushing here, I'm saying one of the carbon or one of the double bond in my arrow group is forming a new bond with the electrophile, and we're breaking the bond between electrophile and X, right? So that's what we see here. We're forming a new bond between your arrow group and the electrophile. Now, in this double bond, on the other carbon that's not making a new bond, we now have a vacancy, which makes a carbocation. The electron in your EX bond goes onto the X atom, making it an anion. So far, so good? And next up, we can think about the electron movement being this way. Now the anion attacks the hydrogen, and the electron goes this way. So we're regenerating the double bond in my arrow group, right? We're forming the new HX bond. We're breaking the carbon-hydrogen bond, and we're regenerating the double bond in here. All right, so this is an example of, you don't know anything about the reaction, but simply looking at the connectivity of your reactant and the product, you can draw the arrow pushing to tell you where the electron is going. And for this reaction, depending on what is the nature of this electrophile can be a halogen, like chlorine, bromine. It can be an NO2. It can be an alkyl group. So depending on the nature of that R group, we call it differently. We call it like halogenation or nitration, Fiedel-Crafts alkylation. So in this case, by understanding what this reaction mechanism, you're actually knowing all these reactions. So that's why we care about reaction mechanism. Now, what is my expectation to you? For this class, since we are not talking about actual electrophilic aromatic substitution, I'm not expecting you to predict reaction, of course, right? So, but what I expect you to know is that if I give you these reactant and product, can you draw the arrow pushing to show the electron movement in how to form this intermediate from the reactant? Okay, so that's one way of asking. Second way of asking is, I could give you this intermediate and I tell you this is the arrow pushing. Can you predict what is the product of this specific elementary step? Like, for example, in this case, thinking about it, what is happening? Now, okay, looking at the electron pushing, electrons in my X is forming a new bond with the hydrogen here. But then my hydrogen will have too many things binded to it, right? It only wants to form one bond. So naturally, I must break this CH bond. and looking at where my electrons in the CH bond go. Okay, it go to the adjacent carbon to regenerate that double bond. So that's my expectation to you. Know how to use arrow pushing as a way to link your reactant and product. Also know how to predict the outcome of an arrow pushing. Yes?
So, if I'm getting this right, you're saying there's like 2 electrons on the X and it makes a bond with H. So
Mhm.
there's 2, I guess, extra electrons on where that E is, and those 2 electrons make a double bond with that.
Right, so we're talking about the electrons in the carbon and hydrogen bond making a new bond here.
Okay, I'm just saying, like, was my logic correct?
Yeah, that sounds right.
Okay.
All right. So that's the overarching goal. And now let's look at some simpler example, because I don't want to frighten people away. Getting started, we went over the arrow pushing rules before, right? So when we're talking about arrow pushing, we're using a curved arrow to show the flow of an electron pair. Now, we were talking about different elementary steps. What is a typical elementary step? Let's say we can have dissociation of a polar covalent bond. Now, in this case, we're dissociating a polar covalent bond. So in this case, let me just say, I know that my B is more electron negative. So, based on the rule of your polar covalent bond, you know the more electron negative will have a somewhat of a partial negative charge. So when the electron is moving in breaking this polar covalent bond, naturally, the electron will be more likely to go onto your molecule, your atom that is more electron negative. All right? So the result will be a cation on A, and then your B will be a anion. And say your B is more electron negative. All right. Or in this case, we're saying both electrons in the covalent bond of your AB molecule will be moved into one atom. The arrow shows the direction of the electron movement, and that direction depends on the electron negativity of the atom. All right. And what is a typical example of a dissociation of a covalent bond? Okay, so let's think about this way. We're looking at on the left, you have a haloalkane. On the right, we are forming a reactive intermediate. And what is the nature of this reactive intermediate? It's a carbocation with 3 R group around it. So this is a tertiary carbocation. And we're forming a Br minus. So in this case, what's our connectivity change? You observe my reactant and the product and say, okay, so we're breaking this carbon-bromine bond. The electron goes onto the bromine, right? So if we're doing the arrow pushing in linking my reactant and products, we end up getting this one. All right, and we're forming a tertiary carbocation. And a bromine or bromide anion. So that's dissociation or breaking of a polar covalent bond. Next example, yes.
So the carbocation that you formed, it's still tertiary even though there's only 2 things attached to it?
This one has 3 things attached to it.
The lone pair counts as something like that?
We don't have a lone pair attached to that carbocation.
Oh, it's the other one, okay.
All right, so for tertiary, you count. This is a SO group, a methyl group, a methyl group. So we have three things attached to the carbocation carbon. That's why it is a tertiary carbocation. So that's our first one, which is dissociation of a polar covalent bond. Next up, what if we have a nonpolar covalent bond? Let's say we have a bromine, that's a BR-BR. So this is a radical reaction. I'm not exactly sure which part you'll first encounter it, but we will discuss it in haloalkanes. So I want you to know that before we jump into that reaction. So when we're talking about a nonpolar covalent bond, this is what we call a homolysis. So we're evenly cleave the covalent bonds. In this case, originally, we have a electron pair in your bromine-bromine bonds. What we're forming is one of these bromine go to one of these electrons go to the left bromine, the other go to the right bromine. Right, so we use a single-sided arrow like this to indicate the movement of one electron, and we're forming free radicals as our product. So the arrow pushing will look like this. So that's a single-sided arrow. All right, and the product of these single-sided arrow are radical species. So it's single-sided because we're only moving one electron, not two. So, for example, we could have this kind of question of asking you, now I have this molecule I start from, and I'm telling you, this is the electron movement. Can you predict the product of this homolytic cleavage of the nonpolar covalent bonds? Now, thinking about the electron movement, what we're getting, we start from two electrons in that carbon-carbon bond. Everything else will stay the same, and I'm just breaking the center bond. And after we break the center bond, you think about, okay, where my electrons go? Now, one electron go to this carbon, one electron go to this carbon. So the product will be a diradical species. All right, don't try to memorize it, just thinking about what is taking place when you have a single-sided arrow. We're saying, okay, one electron go to this carbon, the other electron go to this carbon, and hence you know that's the product. Let's do one more example together. What if we're saying we start from the peroxide species, and I'm telling you we're forming two CH3 oxygen radical, right? How do you use arrow pushing to show the movement of the electron? Well, so we're forming two radical species, oxygen center radical species. So we're breaking the oxygen-oxygen bonds homolytically. So in this case, when we're drawing it, we do one single-sided arrow and to the left oxygen, another single-sided arrow to the right oxygen. Again, my expectation to you is two things. One, if I give you the arrow pushing, tell me what's the product. Two, I give you the reactant and product, tell me how to draw the arrow pushing. And then, after everything, you should be able to tell what's the nature of that reaction. What's the elementary step we're talking about. Okay, any questions before we move on? Yes?
Just with the previous example, does it matter if you put the lone electron inside the square or outside?
It doesn't matter how you draw it. Yeah, there's conventionally, like I like to draw it that way, but it's not wrong if you put it inside. All right, so this is dissociation of bond. So the first elementary step we went over are breaking of chemical bond. You have two ways of breaking the chemical bond. If the bond itself is polar, then you can break it in the heterogeneous or the two electron way, meaning both electrons go to the more electron negative atom. Alternatively, if the bond itself is nonpolar, then you can break the chemical bond evenly. So each electron go to one of the atom. All right, so that's breaking of chemical bond. Obviously, we break chemical bond, we also form new chemical bonds. Yes?
The double versus like single arrows, are those like exclusive to like the full arrow is exclusive to polar and the single side can only happen for
I guess the way to put it is single-sided arrow tells us this is movement of only one electron.
So could that happen?
The double-sided arrow tells us it's a movement of two electrons. And that's the take-home message. Try to memorize it this way instead of linking it to like a breaking of a polar covalent bond, because later on we'll use a double-sided arrow for other elementary steps. All right, so double-sided normal arrow, this one, movement of two electrons. So both electrons go to the end of the arrow. Single-sided electron, movement of one electron. So that's breaking of a chemical bond. Now, obviously, we can also make new chemical bonds. So that goes to next step, which is the formation of a new chemical bond. So typically, in formation of a new chemical bond, again, we always start from the electron sources to the acceptor. Like you never draw an arrow starting from a carbocation. You always start your arrow from an electron source. So in this case, assuming you have a positive charge cation and a negative charge anion, right? So you have a pair of ions. You're forming new chemical bond between the cation and the anion. So my electron pair moves from my anionic B to my cationic A, right? So the direction will be coming from B to A. We're moving the electron pair, so we're moving both electrons, and hence it is a full arrow. So that's what we end up getting, A and B. So a typical example of this kind of arrow pushing are our acid-base chemistry. So thinking about acid-base chemistry, this is something we did before. You have a H plus, you have OH minus. Well, we're forming a new chemical bond here. So the arrow pushing goes like that, right? It comes from the electron pair pointing towards the electron positive or cation. It can be a full, like H plus and OH minus to form a neutral species. It can also be between my Lewis acid base. So again, this one, I give you my reactant and product. Can you use arrow pushing to link them? Now, in this case, on the left, this is my Lewis acid. And remember, what is a Lewis acid? That's electron pair acceptor. Right. And on the right, we have my Lewis base and electron pair donor. Yes?
What's the difference between Bronsted and Lewis?
Okay, what's the definition of Bronsted acid and base? So Bronsted acid is proton donor. Bronsted base is proton acceptor. All right, so in Bronsted acid base, we're always talking about transformation of a H plus. For Lewis acid base, now for example, in this case, we're talking about transportation of an electron pair, not necessarily involving an H plus. So if you want to link the reactant and the product in this case, this is the electron movement we are doing. But in the product we are forming, now my aluminum has 4 different things attached to it. So it's not a neutral species. It will have a formal charge on the aluminum. And for nitrogen, we only have 4 things around it. So your nitrogen will have a formal positive charge. All right. So far, we're only drawing 1 arrow at a time because we're only talking about either a bond breaking or a bond formation process. But in reality, these reactions can be more complicated. You can have substitution reaction. So that's our next example. So a substitution reaction is simultaneously breaking and forming of 2 chemical bonds. So again, in this case, I'm giving you on the left, this is my reactant. On the right, that's my product. All right. And I'm giving you that my B is more electron negative than A. So how do you use arrow pushing to predict, or how do you use arrow pushing to show the movement of electrons in this substitution elementary step? Now thinking about it, on the left, we have AB bond. On the right, the AB bond is being cleaved. So this is what we know. In the reactant, the X and A doesn't form a bond, but in the product, your X and A forms a new chemical bond. So we're forming a chemical bond, we're forming the AX bond, at the same time breaking the AB bond. All right, so how do we do the arrow pushing? We do it from the electron source to the electrophilic site, and then push the chemical bond in your AB covalent bond into your electron negative atom B. And we end up forming a new AX bond and breaking the AB bond simultaneously. All right, and this is linking to our previous practices of identifying nucleophilic and electrophilic site of your molecule. Let's look at an example together and then we'll take questions. The example we have here is, let's say we have a OH minus with an anionic charge. We say that can act as my nucleophilic site. And we look at a haloalkene. So my carbon is directly attached to an electron negative atom. So my carbon is relatively electron positive. My chlorine is Cl minus, or my carbon is electrophilic. All right, and how does the electron move? We are forming the new carbon-oxygen bond, and we are breaking the carbon-chloride bond. So when pushing the electrons, you start from the nucleophile, push it onto the carbon. So we now form my new carbon-oxygen bond, and then push the electron onto the chloride. So the key here is to think about where is your electron while doing it? Are we making the chemical bond we want? Are we breaking the chemical bond we want to break? Okay, any questions before we move on? Yeah.
Are the potential charges, like if we're doing a reactant in the product, do you want to draw the potential charges?
Well, I draw the partial charges because I want to demonstrate this carbon is an electrophilic site. No, it's not required, but I highly recommend you do that before you get very familiar with identifying nucleophilic and electrophilic sites. All right, so that's a substitution reaction. And so far, we only talked about single bonds. The same rule will also apply to double bonds. So we have 2 different kinds of reactions that can take place with a double bond. So likewise, we can have the nucleophilic addition to a polar double bond. So what is a polar double bond? Well, you can easily think about like a carbonyl group, right? So your carbon is electron positive, your oxygen is electron negative. We went over that several times. So in this case, let's say my A is electron positive, my B is electron negative. So in this case, when this kind of addition takes place, it's the same kind of addition. Now you start from the nucleophile. The nucleophile attack the electrophilic site, and the electron got to push onto the electron negative atom B. So we're forming a new AX bond, at the same time breaking the pi bond of your AB. All right. And in reality, what does it look like? Now, thinking about you have a OH minus, and then you have a formaldehyde. Let's do the same analysis. On the left-hand side, we have a oxygen that's anionically charged. We know this is nucleophilic. Right. And then we look at your carbonyl group, and your oxygen is electron negative, your carbon is electron positive. So when pushing the electrons, we start from the anionic oxygen onto the electron positive carbon, and then the double bond got to move onto the oxygen. What we end up getting, we're forming a new oxygen carbon bond, so that's where your new oxygen carbon bond is. And this double bond now being reduced into a single bond. The electron ends up on the carbonyl oxygen. All right. So this is the anionic example. Alternatively, your nucleophile might also be a neutral species. So in that case, let's assume I have an NH3 where the lone pair is, again, acting as a nucleophile. So likewise, my lone pair, nucleophilic lone pair, attack the carbonyl carbon, and the electron in the double bond got to push onto the oxygen. What do we have? We end up having my nitrogen carbon bonds being formed, and then my nitrogen will have 4 different things around it. We have a formal positive charge on the nitrogen. The electron in the double bond ends up on the oxygen, so we have an anionic oxygen there. All right, and this is called a zeta ionic intermediate. All right, and one more type of elementary step we'll commonly see in organic chemistry, which is again a double bond. So in our previous discussion, we were talking about the pi electrons of this AB double bond, so maybe like a carbon-carbon double bond, can also act as nucleophilic. Right, so the pi electrons of your double bond can also act as a nucleophile. In this case, when you put this double bond around an electrophile, they can act as a nucleophilic addition onto the electrophile. And we end up forming some kind of A, B, and E. Sorry, this should be E. Right, so we are breaking this double bond, or we're reducing this double bond into a single bond and forming a new bond with the electrophile. Now, obviously, there is a selectivity issue. Like, do I want my positive charge to be on A or B? And that's why at the beginning of the class, we talked about stability of your carbocation. All right, so for example, if we have an alkene like this, we have a proton. So in this kind of reaction, my double bond is my nucleophile, my proton is my electrophile. So when doing the arrow pushing, we can potentially form two different kind of products, having the hydrogen adding onto the terminal position or the internal position. Now, obviously, this one on the top with your hydrogen forming a bond with the terminal carbon, you're getting a tertiary carbocation. But if your hydrogen is forming a new bond with the center carbon, you are forming a primary carbocation. And among the primary and tertiary carbocation, the tertiary carbocation is more stable, and thus being our major selectivity pathway. Yes. So today is an intermediate class. We will start to use whatever we discussed today in actual reactions, starting from next lecture. So at the end of this lecture, you'll see several practice problems. I highly recommend you try them out. We will be using them more often, starting from next lecture when we talk about real chemical reactions. All right, see you Friday.